Hello, this is the section 3.3 lesson. In chapter 2, when we talked about discrete random variables, we talked about certain types of distributions like the hypergeometric and the uniform and the binomial distributions. Each of those distributions described random variables that apply to certain types of random experiments. Well, we can do the same thing with continuous random variables, and so in this section we're going to introduce two of the simplest types of continuous distributions, the uniform and the exponential distributions. Now in chapter 2 we talked about the uniform discrete distribution, and the basic idea there is that all the values of the random variable were equally likely. Well, the same basic idea is true for a continuous random variable. So here's the formal definition of a continuous uniform distribution. A continuous random variable x has a uniform distribution if its PDF is given by this. And so we have a less than b or any real numbers. Those are the two parameters of this distribution. And so the PDF is 1 over b minus a for x between a and b, and 0 otherwise. So b and a are constants, so that means this fraction here is a constant. So the basic idea here is that a uniform distribution has a constant PDF. Now the phrase x is u of a comma b and the phrase x is uniformly distributed over a comma b means that x has this type of distribution. So in this symbol u of a comma b we denote that it's uniform and the values of its two parameters. We're going to see this notation come up a lot in the rest of the semester. So here's the graph of the uniform density function. So here's x. Anything less than a, the PDF is 0. Greater than b, it's equal to 0. And then between a and b, we have a constant value 1 over b minus a. And so we see from the density curve that the probability that x takes on values close to a is just as likely as it takes on values close to b. And again, that's the basic idea behind the uniform distribution. Now one thing we like to do in chapter 2 was define formulas for the mean and variance of a random variable given its parameters. Well, we can do the same thing for continuous distributions. And so here's a formula for the mean of a random variable with a uniform distribution. So by definition we take x times its PDF and add it up over all values of x. So we integrate from a to b. Now 1 over b minus a, that's a constant, so we integrate x squared, plug in our limits, do a little bit of algebra, simplify, and so here we get this nice, neat, simple formula for the mean of a uniform distribution. Now we can find similar formulas for the variance, b minus a squared over 12, and then here's a formula for the moment generating function. The derivations of these formulas are left as exercises. So to illustrate a use of a uniform distribution, let's look at this example. The owner of a local gas station observes that customers typically purchase between 5 and 20 gallons of gasoline at each fill-up, and that no amount is more frequent than any other. If gas costs $2.50 per gallon, find the probability that a randomly selected customer spends more than $30 on gas. Okay. So the key phrase here to note is that no amount is more frequent than any other. So that means that all these values between 5 and 20 are equally likely. That's an indication that we're working with a uniform distribution. Okay. So let's define the random variable x to be the number of gallons purchased by a customer. And we're going to assume that x is uniformly distributed with parameters 5 and 20. So in other words, x takes on any value between 5 and 20, and no value is any more or less likely than any others. That's a reasonable assumption based on the description of the scenario. Okay. So that means that the PDF of x is 1 over 20 minus 5, which is 1 over 15 for x between 5 and 20, and it's equal to 0 outside of that interval. But now we're not really interested in the amount of gas purchased by a customer, we're interested in the amount of money spent by a customer. So let's define this new random variable y to be equal to the amount of money spent by a customer. And then in terms of x, y is equal to 2.5x because each gallon costs $2.50. And so we've defined this new random variable y in terms of this other random variable x. Now we want to know the probability that the customer spends more than $30. So we want to know the probability y is greater than 30. Well, in terms of x, that's probability that 2.5x is greater than 30. So now inside of these parentheses, we can divide both sides of the inequality by 2.5 to get the probability that x is greater than 12. Well, now we know how to calculate this probability. All we have to do is integrate the density function of x over the interval from 12 to 20, because x can't go any bigger than 20, or at least based on our assumption. And so now what we have here is a constant integrand. And so to find the value of this definite integral, we take the constant integrand times the width of the interval. We do that arithmetic, and we get our probability of about 0.533. So there we go. That's all there is to working with uniform distribution. Our next definition, we're going to define an exponential distribution. So random variable x has an exponential distribution if its PDF is given by this. So we have one parameter lambda, which is some positive number. The PDF is lambda times e to the negative lambda x for x greater than or equal to 0 and 0 otherwise. Now, one use of an exponential distribution is that it describes the waiting time between occurrences that are described by a Poisson distribution. Now, justification for this is given in the textbook, but I won't discuss it here. Now, the parameter lambda in both the Poisson distribution and the exponential distribution has the same meaning. It's the average number of occurrences per interval. So here's a graph of the exponential distribution. We see that when x equals 0, the value of f of x is equal to lambda, and that as x gets bigger, the value of the PDF decreases and approaches 0. And so what we see is that the density curve is tall, close to x equals 0, and it's short for larger values of x. So that means that there's a large probability that x is going to take on values close to 0, and a very small probability that it's going to take on large values. Okay. Now, we can derive formulas for the moment generating function, lambda over lambda minus t. The mean is 1 over lambda. The variance is 1 over lambda squared, which means that the standard deviation is 1 over lambda. So what's interesting here is that the mean and the standard deviation of a random variable with an exponential distribution are both equal to 1 over lambda. The CDF, we can derive a very, very simple formula for the CDF. Here we show, capital F of x, probability x is less than x, which we integrate from negative infinity to x, f of t. But x can't go any less than 0, so integrate from 0 to x, dt. And remember, lambda is a constant, and so we find the antiderivative, plug things in, and here we get a very simple formula for the CDF, 1 minus e to the negative lambda x for x greater than 0. And this is equal to 0 for x less than 0. Okay. And then another common type of probability that comes up with exponential distribution is the probability that x is greater than x, and a very simple formula for that is e to the negative lambda x for x greater than 0. So to illustrate a simple example of this, suppose a manufacturer of electrical wire observes a mean of 1/2 defect per 100 feet of wire. Find the mean distance between defects in feet, and find the probability that the distance between one defect and the next is less than 125 feet. Okay. Now, here we're going to assume that the number of defects per foot has a Poisson distribution. Here a defect is an occurrence, and a foot of wire is an interval. So this seems like a reasonable assumption. So Poisson distribution, lambda is the average number of defects per interval, and so we take our given half a defect per 100 feet, and so that gives us an average of 0.005 defects per foot. Okay. Now we're really interested in the distance between defects, and so let's let x equal this distance. Now we could think of x as being the wait time between defects. Put that in quotes because there really isn't time involved here, but we could think of this as though it's a wait time. So once we realize that this is like a wait time, then based off the argument that we just made, x has an exponential distribution with parameter lambda equals 0.005. And so once we know what type of distribution x has and the value of its parameter, then we can calculate everything we need to know about this random variable. So according to the formulas that we just gave, the mean mu is 1 over lambda, which comes out to be 200. So there's an average of 200 feet between successive defects, which makes sense because we had a half of a defect per 100 foot. So that kind of makes sense. Now, we can also calculate the probability that the distance between defects is less than 125, which is the probability x is less than 125, which is the value of the CDF evaluated at x equals 125. We plug that into our formula for the CDF, and we get our value there. So there's about a 50% chance that the distance between defects is less than 125 feet.